We use stacks in all parts of our lives. Did you know a stack is a type of data structure and it's used to implement a type of algorithm called a depth-first search? Would you like to see? Let's look at the depth-first search, the DFS algorithm. Here we have an example tree. We can see the same elements we looked at when we looked at the breadth-first search. Now the difference here, we start off with the root node, which is the same. First node to the left is 2, but this is the depth-first search. So after 2, we go down the next level. So it's the first element as we go down the tree. So from the element 2, we go to 4, and then we go to 5. Now you can see here, the left hand side of the tree, every element is visited before the right hand side. So we continue, we have 3, then 7, then 8. So that completes the tree. Another example, we start off with the root node with 1. We go to 2. The breadth first search, we'd look at 4 and 5, but depth first, we go down to 3. Then 7, then 8. And then finally we do visit the 4, then the 5. How about a task for you? What is the order of the elements with a depth first search? Tell us what the order of the elements that will be visited using the depth first search. And we'll look at the solution later in this video. Now let's have a look at an example how we would implement depth first search. So here we've got another tree. We're going to use the depth first search and we're going to implement this using a stack. So here we've got a stack. We've already put in the root element 1. It's like a stack of books. If you put a book on top of a stack of books, if you need to take something off, you need to take off the top book. And in the stack it's the same in programming. We start off putting elements in the stack, and if we want to take them out, we take out from the top. So we can see we've got child elements 2, 9 and 10. When we put these in the stack, we put them in reverse order. We're going to put in 10, then 9 and 2, because 2 is the element we want to access next. We've popped out 1 because we've already visited that. And now we've got 10, 9 and 2 in the stack. As I said, we take from the top of the stack. So our next element that we look at is 2. Now we take out 2, it's now visited. The children were 3 and 4. They go in the stack in reverse order. So now in our stack we have 3, 4, 9 and 10. So we now visit node 3, which doesn't have any children. Then we look at node 4. Node 4 has children 5, 6 and 7. Remember, reverse order. Now we access the element with 5. That has the child node of 8 that goes to the top. That has no children, so it comes straight out. And you can see now that the elements we have remaining are 6, 7, 9 and 10. And none of these have any children nodes. So these will just come straight out, and we'll put that in a list of all the visited elements. So we can see the order there. We had 1, 2, 3, 4, 5, 8, 6, 7, 9 and 10. Here is a directed graph. Now we've used this because we're going to go down the depth first, so we want to stop somewhere. So the graph we could see goes from left to right, and we can see that we're going to start off with the element 1 as the root node. So let's start off using a depth first search on this graph. So the root node you can see we've highlighted as 1. Now we're going to show you the paths. Here we're going to go to 2. So the children nodes of root node 1 are 2, 5 and 3. But with a depth first search, once we visit 2, we then go to 4 then 8, and then 10. There's no children of the node with 10. That element doesn't have any children. Notice here that the element 2 goes to 4 and 7. First of all, we went to 4 and we carried on that path through 8 and 10, but now we go to the 7. So all of the children of 10, 8, 4 and 2 have been visited. So the second child of the root element, so number 5 was the second child of the element 1. All of the other nodes to the left of that have been visited. So now we go to 5, which has no new children. 7's already been visited. And then finally you can see we can go from 1 to 3 to 6 and then finally to 9. So the order of the depth first search on this graph was 1, 2, 4, 8, 10, 7, 5, 3, 6, 9. Now let's have a look at the code. Here is the tree that we used in the breadth first search. You can see we have the keys and the values. The values are a list of child nodes in the tree and it's part of a dictionary. So that's how we define the tree. Now with that, we've got the depth first search, which is similar to the previous video's breadth first search. We have the stack rather than the queue. We still append each node. The difference really is we put the children in reverse order. And if a child node is not in the stack already and it's not been visited, we append it to the stack and then we pop the stack when we visit each element. The depth first search code is very similar to the breadth first search code. We have the tree, the dictionary with the keys and the values as lists with the children element, and then we look at our code. Again, we pass the tree and the first node. We keep the visited elements in a list. So we visit the stack in this case with the depth first search. We take out the first element. Then we add that to the visited, same before. And as we said, the difference really is that we put in the children in reverse order into a stack. And obviously with the stack, as in with Python list, we take at the end of the list or the top of the stack. So that's the difference from the breadth first search. Check the children not already been visited and not in the stack already, and that's pretty much it. You can see the output from this code. We can run it again. We can see, and this matches the example that we've already explained earlier in the video. Just for interest, we can quickly look at the code for the graph. Here, because it's not a tree, we can't use a dictionary, so we use the OO code and we add each edge to a graph. So this code, we can see we've used the default dictionary here, and in the graph we add the edges and we add the nodes, and we have the depth first search code here. Essentially it does the same. We look at the visited nodes, we have the neighbors rather than the children, and when we run that, let's have a look. We can see in this case we just have the order that the elements come out. When we looked at the graph, the order was 1, 2, 4, 8, 10, 7, 5, 3, 6, 9. So that's just a quick look on some code of the depth first search on the graph traversal. You can see here, this is our output from the code, and this is our output in our example from the example tree that we followed previously. Let's have a look at the solution to the task. Here we had our example tree. Now what order will the elements be visited in? So we start off with 1, and then we put in the child nodes in reverse order. So now we're going to pop 2. Again, 7 and 6 will go in, visit 6, then 7, then 10, then 3, then 8, then 4, then 9, then 5. So that was the order that we visited with a depth first search. 1, 2, 6, 7, 10, 3, 8, 4, 9, 5. Did you get that correct? If you did, well done. There is a great new opportunity for anyone interested in learning about Python or any other areas of computing. In the next year, new courses will be added to the Alps Academy, and they will be available to you for free. Written by university professors, they will be specifically designed for international students, which means they'll be easy to understand using simple language. They will even be helped to improve your English if you're interested. How can this help you? Well, leave a comment. Any suggestions you make could be turned into a course. Motivated learners deserve equal access to opportunities. Help us to help you.